The Firth of Tay Bridge collapse. This railway bridge in Scotland collapsed on a stormy night in December 1879 while a passenger train was crossing it, killing all 75 people on board. The bridge had been considered one of the great engineering achievements of the Victorian era when it opened just 18 months earlier. It was the longest bridge in the world at the time and had been personally inspected and praised by Queen Victoria. The collapse was caused by a combination of design flaws, poor quality cast iron in the structural columns, and inadequate accounting for wind loads. The chief engineer Thomas Bausch was found responsible and died in disgrace less than a year later. The disaster completely changed how engineers approached wind loading calculations for bridges and led to the introduction of formal standards for bridge testing in Britain. The Quebec Bridge collapse. This bridge over the St. Lawrence River in Canada collapsed twice during construction, making it one of the most catastrophic engineering failures in North American history. The first collapse in 1907 killed 75 workers when an arm of the cantilever fell into the river due to miscalculations in the weight of the steel structure. Rather than redesigning the bridge from scratch, engineers returned to the same basic design with modifications, and during the second construction attempt in 1916, a central span section fell while being raised into position, killing another 13 workers. The bridge was eventually completed in 1917, but the two disasters reshaped engineering education in Canada in a lasting way. Canadian engineers to this day wear an iron ring on their working hand as a reminder of the human cost of engineering failure, a tradition started partly in response to this disaster. The Malpasset Dam failure. This arch dam in southern France collapsed on the night of December 2, 1959, releasing 50 million cubic meters of water into the valley below. Within minutes, the flood wave destroyed everything in its path, killing 423 people in the town of Fréjus and surrounding villages. The dam had been considered a technical triumph when it opened in 1954 as the thinnest arch dam ever built. The failure was caused by water seeping into a fault in the rock foundation that had not been detected during geological surveys, which caused the left abutment to shift and the arch to fail. The disaster led to a complete overhaul of dam safety practices in France and internationally, including requirements for detailed geological surveys of foundations before construction begins. The Ronan Point collapse. This apartment tower in London suffered a partial progressive collapse in May 1968 when a gas explosion on the 18th floor blew out a load-bearing wall panel. Because the building used a construction system where each floor slab rested on the one below rather than being tied into a structural frame, removing one panel caused the floors above to fall, which in turn caused the floors below to collapse under the impact. 4 people were killed and 17 injured. The building had been completed just 2 months earlier and was considered a modern, efficient housing solution. The collapse revealed fundamental weaknesses in the large panel system construction method that was being used widely across Britain and other countries at the time. Building regulations were changed, but many buildings constructed using the same method remain standing today. The Hyatt Regency Walkway collapse. This disaster in Kansas City, Missouri in July 1981 remains the deadliest structural collapse in American history outside of the September 2001 attacks. 2 suspended walkways in the atrium of the Hyatt Regency Hotel fell during a crowded dance event, killing 114 people and injuring more than 200 others. The walkways were hung from the ceiling using vertical rods, and a design change made during construction had doubled the load on a critical connection point by altering how the rods connected to the walkway beams. The change had been communicated between the engineering firm and the fabricator in ways that were unclear and inadequately reviewed. Investigations afterward found that even the original design was insufficient to meet the building code. The engineers responsible lost their professional licenses. The Tacoma Narrows Bridge. This suspension bridge in Washington state opened in July 1940 and collapsed just 4 months later in November of the same year after developing violent oscillations in a moderate wind. The collapse was captured on film and became one of the most studied events in the history of structural engineering. The bridge had earned the nickname Galloping Gertie shortly after opening because of its tendency to sway and ripple even in light winds. Engineers had been aware of the motion but considered it an aesthetic quirk rather than a safety concern. The collapse was caused by a phenomenon called aeroelastic flutter, where the deck design inadvertently created conditions for the wind to reinforce its own oscillations rather than dampen them. Bridge design was permanently changed as a result, with aerodynamic testing becoming a standard part of the engineering process. The Camano Powerhouse Slide. This hydroelectric facility in British Columbia was nearly destroyed in 1961 when a massive rock slide above the intake tunnel threatened to collapse the entire water delivery system for one of the largest aluminum smelters in the world. The slide had been triggered by blasting during construction of the project and sent millions of tons of material down the mountainside. Workers evacuated in time and nobody was killed. But the damage to infrastructure was severe. The recovery required engineering solutions that had no precedent, including drilling relief tunnels through active slide material while the mountain continued to move above them. The story received almost no public attention at the time and is largely unknown outside of the hydroelectric engineering community, but it is studied as a significant case in geotechnical risk management. The St. Francis Dam failure. This concrete arch gravity dam north of Los Angeles failed on March 12, 1928, releasing 12 billion gallons of water into the Santa Clara River Valley. Between 400 and 600 people were killed, making it one of the deadliest civil engineering disasters in American history. The dam had been designed and built under the supervision of William Mulholland, one of the most celebrated water engineers in the American West and the man responsible for bringing water to Los Angeles. Investigations showed that the geology of the canyon walls was far more unstable than surveys had suggested, with one side resting on ancient landslide material that softened and failed when saturated. Mulholland accepted personal responsibility at the inquest, and his career and reputation never recovered. The disaster ended the era of major dam construction by a single self-taught engineer without formal peer review. The Laufenburg Bridge mismatch. This bridge across the Rhine River connecting Germany and Switzerland was completed in 2003 and immediately discovered to have a 54-centimeter height difference between the two halves. The two construction teams, one working from each bank, had used different sea level reference points. Germany calculates elevations relative to the North Sea, and Switzerland calculates them relative to the Mediterranean. And the teams had failed to account for the 27-centimeter difference between those reference levels. When the adjustment was multiplied by the specific topography of the crossing, the result was a visible and embarrassing step in the completed roadway. Correcting the problem required expensive modifications to the approach sections on both sides. The project became a case study in the importance of verifying shared reference data before large transboundary construction projects begin. The Leaning Tower of Pisa construction. This bell tower in Italy has been leaning almost since its construction began in 1173, and the story of how it ended up that way is one of the longest engineering dramas in history. The lean began almost immediately because one side of the foundation was built on soil that was too soft to support the weight of the structure. Construction was halted multiple times over the following 2 centuries due to wars and political disruptions, which ironically gave the soil time to compress and stabilize enough to prevent total collapse. By the time it was completed in the 14th century, the lean was already pronounced. Over the following centuries, it continued to tilt further, and by the late 20th century, engineers determined it was in danger of falling. A major stabilization project completed in 2001 removed soil from the high side to allow the tower to settle back slightly, reducing the lean to a safe angle.